Hello, my name is Alec Davis from the University of Manchester in the UK. In this talk, I will be presenting the investigation conducted by me and my colleagues at the University of Manchester and Cranfield University into a novel recrystallisation mechanism that presents in interpass deformed titanium components built using Wire-Arc Additive Manufacturing, or WAAM. First, it seems prudent to give a quick overview of titanium additive manufacturing, or AM. The focus of titanium AM was initially on powder bed processes, where small, complex components are built in contained chambers, given a significant cost and weight reduction over conventional processes. However, these part sizes are restricted by their manufacturing chambers and slow deposition rates. Direct energy deposition processes with a high power input allow faster build rates and larger components, but by sacrificing component complexity. Wire-Arc AM, or WAAM, is one such process that uses wire feedstock and typically a plasma power source to deposit layers of melted wire on top of one another as a series of welds. It has very high build rates and no restriction on component size. However, by scaling up the component size by using a higher power input changes the material solidification behaviour. With a laser source, the cooling rate from liquid is around 10 to the 4 degrees C per second. An electron beam source reduces this to 10 to the 3 degrees C per second, and even though there is little change in the melt pool size, shown at the top of this slide, with this cooling rate reduction comes a change in the solidification microstructure. Titanium first solidifies into the cubic beta phase from the liquid, but then transforms to the alpha phase through the Berger's orientation relationship as cooling continues. In titanium, 6 weight% aluminium, 4 weight% vanadium, or Ti64, the only titanium alloy included in this presentation, this transverse temperature is about 980 degrees C. The EBSD maps shown beneath the melt pool diagrams are beta phase maps, reconstructed from the room temperature alpha phase data. These maps show that the reduction in cooling rate produces a coarser and more columnar beta grain structure that can reach centimetres in size and has a strong 100 fibre texture parallel to the build direction, shown in the pole figures below. WAAM has a significantly higher power input and therefore much larger melt pool and lower cooling rate of 100 to 1000 degrees C per second, producing a fully columnar beta grain structure. This columnar grain structure produces significant scatter in the mechanical properties, particularly the elongation in the horizontal direction, which is parallel to the heat source travel direction. Since a major target application of titanium AM components is aerospace, which cannot tolerate significant data scatter, unreliable properties are a serious problem. However, my colleagues at Cranfield University discovered that if you introduce a cold deformation step between each deposited wire layer in WAAM by, say, rolling or peening, the beta grain structure is refined through recrystallisation, shown in the EBSD maps here, and the texture is markedly weakened, shown in the pole figures at the bottom. What makes this recrystallisation particularly interesting is that it requires only a reduction as little as 8% during rolling, when typically about 50% is required to activate recrystallisation. That is, this is a non-conventional recrystallisation mechanism. And, as one would expect, the grain refinement produces more reliable properties, demonstrated here by the stress-strain curves for the refined microstructure on the right. We investigated this interesting recrystallisation mechanism in 3 stages. 1. By observation, to determine the conditions where the recrystallisation was active and to quantify the grain refinement. 2. We then used our observations to propose possible mechanisms for this novel recrystallisation. And 3. We designed new experiments to eliminate the possible mechanisms down to 1. For our observations, first, we had to design a method of replicating the interpass deformed WAAM process so that we could control the deformation and the thermal cycles. For this, we used a plane strain compression rig for cold deformation, which is representative of the deformation in process, and we used our induction dilatometer to achieve the high heating rates that the material experiences during the WAAM process, which is about 500 degrees C per second. On the right are a series of EBSD maps of a sample in the as-built condition with a columnar structure, which, at this scale, is effectively a single crystal. Next is a map after deformation, and finally, after a heating cycle into the full beta phase field showing the recrystallization. The high heating rate is intrinsic to WAAM. When we used a low heating rate instead for our simulations, it had a drastic effect on the recrystallization. The EBSD maps in the middle here show the poor grain refinement achieved when a heating rate of 0.3 degrees C per second is used instead of about 650. We also used an ETMT to simulate the WAAM process, which involved grips cooling the matchstick sample ends, as shown on the right here. This again demonstrates the impact of heating rate on the grain refinement, but also that transformation into the full or near full beta phase is required for the recrystallization to occur, as shown by the lack of refinement in the cooled regions. By conducting an in-situ heating XRD experiment, where the respective phase volumes and grain orientations were measured during the full phase transformation during rapid heating, you can see that at low temperatures, the prior columnar beta orientations return that formed during solidification, marked on the graph in red, but then new orientations start to appear during the final stages of the phase transformation above about 950 degrees C. Now, to summarise our observations, and others that I don't have time to include fully, the recrystallization mechanism requires a fast heating rate to operate, it requires at least 9% strain to activate, it requires a fine alpha plus beta room temperature microstructure, which is intrinsic to WAAM, it occurs during the final stages of the alpha-beta phase transformation, and it is independent of tested deformation temperatures and speeds. The low activation strain rules out conventional recrystallization processes, as mentioned earlier. We found no deformation twins in the cold deformed microstructure using high-resolution orientation mapping, shown in the images on the right, which rules out deformation twins as the source of new grains. Since higher temperature deformation suppresses twinning through easier slip activation, if deformation twins were responsible, we should have seen a reduction in grain refinement at higher deformation temperatures, which we didn't. High strain rates can also promote deformation twinning, so a reduction in strain rate should have reduced the grain refinement if deformation twinning was responsible, which it didn't. It seems all this recrystallization mechanism needs is a sufficient amount of dislocations in the microstructure, a high heating rate, and a transformation into the full beta phase. Many EBSD scans were conducted of the recrystallized beta grains in this investigation, and the more we conducted, the more of this peculiar pole figure pattern we saw, which has 4 poles with 4-fold symmetry distributed about the 100 pole directions, tilted away by about 30 degrees. Using our WAAM simulations with the cooled sample ends, we were able to produce a before and after comparison relating single prior parent beta orientations to the recrystallized grains produced within them after heating. On the right here, region 1 shows a prior parent grain, and 2 shows the related recrystallized region. The parent orientation has its 100 pole parallel to the WAAM normal direction, coming out of the page here, and the recrystallized grain texture motif can be seen to be directly related, where the recrystallized grain poles are tilted approximately 30 degrees away from the parent 100 pole. Clearly, there is a crystallographic orientation relationship here. We also investigated this recrystallization through in-situ SEM EBSD experiments using an in-chamber heating stage. Although we could not achieve the high heating rates required, we were still able to obtain some useful data. On the top here, the alpha and beta microstructures at 950 degrees C are shown in the left and right EBSD maps respectively, and a region of new recrystallized grains is magnified. Below, the two common twin boundary types are highlighted over the band contrast EBSD map in blue and red, which show that at 900 degrees C, many 111 type twins were present through the microstructure and at the recrystallized grain boundaries. This led us to believe that twinning was involved in the mechanism. Returning to the texture relationship, we modelled these two twin types using the parent orientation in region 1 here as our starting point to try and replicate the texture motif. A single twin rotation yielded no results, but a double twin rotation gave us something similar to what we were seeing, minus the starting orientation in the centre. This strengthened our belief that twinning is responsible for the recrystallization mechanism. This is a schematic of our recrystallization mechanism proposal. A shows the alpha plus beta lamellar microstructure with a sufficient density of dislocations. During heating, the beta lamella regrow into the alpha and encounter the dislocations. This alpha-beta interface and dislocation interaction produces a stacking fault, which evolves into an annealing twin, which then grows within the beta lamella and into a new strain-free grain shown in B. This strain-free grain has a growth advantage over the deformed surrounding beta and quickly consumes it. While the alpha remains, this new beta is pinned, shown in C, but towards the end of the phase transformation, the alpha is completely consumed and the new beta grain grows and consumes the remaining deformed beta. Since the lamellae are of a manner of hundreds of nanometers, a macroscale region containing millions of lamellae can be fully refined with 100 micron diameter grains with only a small chance of these stacking faults occurring. However, it is not clear why a double twin is required. Since a double twin operation produces many more possible orientations, these rotations may be required due to the restraint from neighbouring lamellae. To summarise, we think annealing twins are responsible for the recrystallization mechanism, and our models point to a double twin rotation, but we still cannot completely rule out a mechanism related to local lattice rotation rather than twinning, like the example on the right from Pilchak and colleagues. So, we designed a new experiment to rule out lattice rotation. Our single crystal texture motif was produced by compressive deformation. If lattice rotation was responsible for the recrystallization, a change of deformation mode to tension will change the resultant texture. If twinning is responsible, a deformation mode independent mechanism, the texture motif will remain and lattice rotation can be ruled out. So, we sectioned a tensile sample from a WAAM wall with a columnar beta structure and strong texture, which was confirmed by EBSD of the sample grip shown here. We then tensioned the sample to fracture and rapidly heated it above the beta transverse temperature. We then took an EBSD map of the region on the left by the fracture surface where the strain was highest. This is what we found. This is an EBSD map in inverse pole figure colouring with reference to the WAAM build height direction. On the right, in the low strain region, the columnar structure remains. As the strain increases, recrystallization occurs. The columnar structure, marked by A, has a typical strong 100 fibre texture. The region directly related to this parent grain, B, again shows the familiar texture motif and confirms our twinning mechanism proposal. Interestingly, we also found further texture development at the higher strains achieved in this sample. You can see a colour transition in the EBSD map from right to left. Red in the parent grain region, purple and blue in the twin recrystallization region, but then it transitions back to red towards the fracture surface on the left. This corresponds to regions C and D, where the texture evolves back to a 100 fibre texture, but with a larger spread than that of the parent orientation. This shows that conventional recrystallization returns at higher strains, probably because the high dislocation density pins the alpha-beta interfaces, stifling new grains being generated by their movement. And finally, you'll have noticed the asterisk added to any inclusion of the word confirmation. I added this since we have yet to witness the twin mechanism in action directly, since it occurs during a manner of milliseconds, and we currently do not possess the means to capture this. Furthermore, we admit that there may be something we haven't thought of yet. As such, we plan to follow up this work with some modelling to work out a precise mechanism where annealing twins can form in this way, and investigate the reason for double twinning over single. Thanks very much for listening to this presentation. Please see this slide for my conclusions, and pause the video and read at your own pace. And see this slide for the papers published to document this research.